Hello, my name is Caleb Schumann. I'm Ag Engineering with a focus in Machine Systems.
Chris Ziga, Ag Engineering with the focus in Machine Systems.
I'm Austin Fisher with the focus in Machine Systems Engineering. Together we comprise the hydraulically powered grain cart axle with tracks and variable motors team. Our primary sponsor for this project was Terra Drive Systems, with our contacts being Brad Meyerholtz and James Smith. Within this project we had three primary objectives, and the first of these was to create a Microsoft Excel model to kind of emulate the predicted tractive performance of the cart while it's going through the field under normal operating conditions. So to start off, we had to know the motors that we were using to power the tracks and the parameters that kind of govern them. And from there, we were able to gather data on the cart system and track itself, the topography of the land, and then the soil conditions themselves. From there, we were able to kind of compile all those using several empirical formulas that have been compiled by industry professionals and then some industry rule of thumbs. And we were able to throw that all together in a model and then kind of output the predicted tractor performance and whether that tractability would be adequate for each specific tractor cart environment combination. So with that, I'll pass it on to Caleb to talk about the next objective.
For the hydraulic system, it was very interesting when we started doing some calculations because there's two loading scenarios that we thought that we should cover. One is the most important for it as engineers is the worst case load. That occurs actually on firm soil and or concrete. But for the farmer, the worst case scenario that they're going to run through is mud. So we had to make sure that we had to differentiate between the two to make sure that we were actually designing for the right load. So we went through and did the design. We decided on SAI Hydraulics TV 3.5 with 1,000 zero displacement cc displacement. This allowed for a roughly 100 cc displacement buffer from our worst case loading. We wanted the motors to be providing about 26% of the tractive or propulsive force needed for the grain cart. So that's what we used when we went in and did the calculations like Austin was talking about. The next part that then for our systems, we included two crossover relief valves to reduce any sort of pressure spikes that might occur, as well as using a three Parker two-position bidirectional poppet valves that allow for flow to obviously go back to the motors as when turned on, and then when it's turned off, it allows the flow to circulate through the system and to allow the flow to circulate through the system to prevent any sort of pressure spikes that might occur from just rolling or pulling the grain cart behind it. So our third one was the FEA analysis that Chris will talk about.
So I did fundamental analysis on the axle and spindle that they designed to support the tracks in the grain bin. Basically, we came up with 4 different load scenarios to figure out the stress and deflection for each of these parts. What you see up here is the second load scenario with the fully loaded grain bin and the maximum drawbar that the tractor would receive on concrete. And what you see here is the inside of the axle and the spindle support tube. As you can see, the welds along these gusset plates are below the 90 psi yield strength limit that they had for their filler rods. An area of concern is the stress concentration on the bottom that is resting, the spindle support tube is resting on the bottom face of this axle. This exceeds the material yield that they have for that spindle support tube. Basically, to correct this, we're just going to put a gusset plate on the bottom of that and then give them the stress, the new calculated stress for that. And then right here you see the spindle. The only area of concern for the spindle was right here. As you can see, that is below the 90 psi limit for the welds. And then the next part we did cycle fatigue for each of these parts. We used Miner's rule to find the lowest limit to see if we could actually design this for infinite life. And for 100,000 cycles, it actually exceeds that at 400,000. And so 400,000 also an adequate value for field use as well. And so the design they have fits the needs that they want for the cart, and it's an adequate design.